Streaming is started. I've posted the link in chat. We need a 2-minute break. Okay, let's start at 8:05 then. But this is going to happen every week, yeah? Yeah, maybe we'll start around 8:05 every week.
Hello.
Yeah, hello.
Yeah. Am I? Oh, I think the video was not starting.
Yeah, 8:05 we'll start. Since there was a statistics session just before, someone requested for a break of a couple of minutes. So at 8:05 we'll start.
Okay, sir. Yes, sir.
So in the statistics session, we have been told that instructor sessions recording will be available. Is the same applicable for mathematics sessions also, or is it different?
Could you repeat the question? I couldn't hear you clearly.
No, the question is in the earlier session we had in the statistics, the instructor said that the recording will be available
Yes,
offline
this
for
actually right now it's being streamed, and I've put the link in the chat box as well. It
okay,
will be available on the Math 2 YouTube channel. Instructor sessions will be streamed.
okay, not the TS sessions. Okay, so that's the new.
Week one content might not be available, and I think was an announcement regarding the same not issued. So probably it was or not. I don't know. It's a policy that has been adopted for all courses that live sessions will be streamed.
Okay. There was a
Okay, I think
there was huge confusion earlier that no streaming would be available, but would that
yeah, there were merits and demerits, and
yeah,
we went a bit back and forth, and we decided
right.
this is the best way to go about.
Probably it
All
seems
right,
to be a knee-jerk reaction. We don't have to discuss it.
all right. So in last session, let me start by giving a bit of a recap. So far, I think in week one, you have already seen vectors, matrices, and systems of equations and how to represent a system of equations in a matrix language. So if given a system of equations, you can always write it as this, where in the most general case, you'll have an m cross n matrix, which is also called a coefficient matrix. And then you will have this variable vector, which will be n cross 1. And this is the constant vector. This will be of size m cross 1. So this is a most general form for a system of equations, correct? And then after describing the system of equations, there was a bit of a detour where we started exploring what the determinant of a matrix is. But the determinant of a matrix is a number which makes sense only in the context of square matrices, meaning here you need m is equal to n. For square matrices, there is something called determinant A. And most of the second half of first week deals is concerned with uh, properties of the determinant, how to compute the determinant, and so on. I think up until this point, it has been taken care of. Let's say j is equal to 1 to n minus 1 to the 1 plus j a1j m. Does everyone understand this formula?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So what this essentially says is, if you just take a particular case of 3 cross 3 matrices, where you have, strictly speaking, it is better to write A11, A12, but I'll just use this. If I have a 3 cross 3 matrix like this, how do I compute the determinant? I first look at I look at this first row, and the first element A, I multiply with the determinant of what I get after removing the first row in the first column. That means A times EI minus HF. And then next I take the second element in the first row, which is B, and then I look at this submatrix DFGI, compute the determinant of that, and uh, multiply it with B along with a negative sign. So there is a sign thing that you need to take care of. But at every point, what you need to do is take the elements and multiply it with the submatrix, which is obtained by removing the corresponding row and column. And that is what is just written very compactly over here. So in this formula, we are actually doing it along the first row. The first thing that we'll be seeing in this session is that it is not necessary to only do it along the first row. Was this property also discussed in the last session, that you can do it along any row or any column?
No, sir.
Okay. So suppose I'm given a matrix. Let's say I'll just write some random numbers. Okay. So if I wanted to calculate the determinant of that, how would I go about doing it? Let's call this guy A. Determinant of A is 2 times
2 times 6
minus 6
minus 6
minus,
0 plus minus 1.
just verify that I'm doing the computations correctly. So this is minus 12 minus 9, which is 102, right?
Right, sir.
So,
Yes, sir. Sir, I
so
did
but
not get this. Kindly explain it once more.
this is just a straightforward computation of the determinant. I took the first row. I looked at this 2 is from the first element. 2 times the determinant of this matrix, which is 604 minus 1, which I compute just by doing 6 into minus 1 minus 0 times 4, which is minus 6 minus 0. And then to that, I add the negative of this minus sign comes because of this minus 1 to the I plus j component of it. So there is a minus sign over here. That is what you have to take care of. But other than that, it is just 1 times this the determinant of this submatrix, which is again 0 minus 0. And the last term is plus 3 times the
So
determinant of this
zero,
submatrix.
0 minus 0, right? I mean, if I take 1, then 0, 5, 0 minus 1, right? I mean, is that not the determinant for it? Because I'm
Okay, so this should be, if you want one more step, this will be determinant of 2 times determinant of 604 minus 1 minus
Sir,
1
why 2
times.
times of determinant? Sorry, I'm not getting this.
The first element is 2. So you have to look at the elements in the first column, take each element and multiply it with the submatrix corresponding, the submatrix that you obtain after you delete that row and column. So in this example, 2 is the first element, correct? Over here, I have to multiply 2 with the determinant of this matrix, 604 minus 1.
Okay.
Okay, and then there is a minus 1 times, that 1 comes from over here, minus 1 times the determinant of this matrix, which is 0, 0, 5 minus 1. plus 3 times this matrix, which is 3 times determinant of 0, 6, 5,
Understood, sir.
4.
Got it.
Okay. Here to take each element, look at the corresponding submatrix and multiply that element to its determinant, to the determinant of the submatrix along with the proper sign. So in this case, this will be plus minus plus, the sign that comes along with the number. Okay, so after this, you can go back to this step and then you'll get it. This is how you compute the determinant of A, and that is 102. But one of the properties of the determinants is that you don't need to actually start with the first row itself. There is nothing special about the first row. So just look at this computation in an alternative way. I look at, in this case, the second row, which is 060. I do something very similar, but here the signs may be a little confusing. I'll take a minus. In this case, it doesn't matter because it's a 0. Minus 0 times. I do the same trick, or I do the same procedure, rather. I take a reference as the second row instead of the first row. So what did we do when we expanded along the first row? We did element times determinant, correct? Similarly, we'll
Yes, sir.
do this element times the determinant of this. So that is 1, 3,
3, 4
4
minus 2.
minus 1 plus 6 times the determinant of,
2,
what do we need
3,
over
5
here?
minus 1.
Yeah, this 2, 3, 5 minus 1 minus 0 times the determinant of the last element. So the matrix that I get is 2, 1, 5, 4. But here, what is the advantage? The advantage is that you have a 0 over here and a 0 over here. I don't really need to bother about those terms because 0 times any number is 0 and they'll not add anything to the determinant. All I care about is 6 times minus 2 minus 15. That is 6 times minus 17. And what is 6 times minus 17?
102. Minus 102.
102.
So here you saw that even though we are doing a similar procedure, it is much easier because here we had more zeros. If you have more zeros in a row, you will have lesser computations to do because you will say in this case we had 2 zeros and only one non-zero entry. So all you need to worry about is that non-zero entry times the corresponding submatrix. Yeah, is there a doubt?
So we can also go through the columns, right?
You can go through the columns as well, yes.
Sir, is it possible to do one simple calculation with a 4 cross 4 matrix?
Well, is it not just an extension of the same?
Where I find it difficult is,
Uh-huh.
let's say when we do a 4 cross 4 matrix, the ith element, if we take the determinant, I'm not sure like how the determinant should be there because you will have one additional column for that. That is where I'm finding it.
Okay, let me just complete this and then I'll take up a 4 cross 4 example. I'll probably not do the entire computation, but I'll tell you how to proceed.
Just one determinant is good enough. Thank you, sir.
Yeah, okay. So we see that the determinant over here, while using the first row or the second row, has turned out to be the same, but in the second row, it was much easier to compute. And this is not something particular to this example. This is a property of the determinant that this is just property, let's call it property 1. Computing the determinant can be done along any row or column. The first row or column is just one way to do it. You can compute the determinant along any row or column. But then there is one thing that I have not addressed yet, is the fact that over here I had a plus, minus, plus, which accompanied the entries in the row.
Sir,
But
here
here I
we have
used minus, plus, minus.
here, sir,
Right. So
I to the power of I to I 1 to the power of I plus j, is the answer for this, right, sir? Minus
yes, correct.
1.
Yeah. So what you have to do is, it's not just that, it's not arbitrary that plus minus plus was assigned to this and minus plus minus was assigned to the second row. Whenever you are doing the computation of a determinant along any row or column, the sign that accompanies the ijth entry. So for example, let's see what the sign for this is. What is
Nine,
the this is what is the
2-1,
address of this entry?
2-1.
2-1.
This is the 2-1 entry, or let me just write it as A21. So for
Yes,
A21, the sign is minus 1 to the power 2 plus 1, which is minus 1 to the 3, which is just minus 1.
yes, sir.
So this entry, 6, what is the address of that entry?
8-2.
This is the 2-2 entry, the second row, second column. So the sign that accompanies this is minus 1 to the power 2 plus 2, and that is 1, or it is just plus 1. And similarly, if you take this 0, which is A23, the sign that it gets is minus 1 to the power 2 plus 3,
Sir,
which
I
is
did
minus
not
1.
understand this. Could you please, this power part, -1 to the power 1, I'm not getting it.
So minus 1 to the power I plus j is what you have to do. Okay, so when you're considering the when you're considering the entry, this 0, for example, this one, what is the entry? What is the row and column? What are the coordinates of that entry? It is A21, right? That part you get.
Yes, 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 sir.
So it is A21. So the I for that entry is 2 and the J for that entry is 1.
Correct, sir, correct.
So what is the sign that comes along with A21 is minus 1 to the power 2 plus 1. So in general, it is minus 1 to the power I plus j. If I have Aij, the sign that comes along with Aij is minus 1 to the power I plus j.
Okay.
Okay. Now, when you're computing the determinant, what are you doing? You're taking an entry and multiplying it with a certain determinant of a submatrix, right? And what sign should I put over here is dictated by what is the minus 1 to the I plus j corresponding to the coordinates of this entry.
So pardon
Right?
once again, please.
Okay. Let's do another example where I do for the third row.
So
Let's
just
say I just take.
for simplicity, I mean, if we take the step 1 as you did, and then
Mhm.
start with plus, and then next will be minus, then next will be plus, likewise, right? For every
Yes.
alternate sign.
Yeah, that is there. You can just do plus minus plus minus plus minus plus minus plus. This is what you're suggesting.
I mean, just the previous, the first, the way you first described the first approach, which I see first it is positive, then it is negative, then again positive, again negative, likewise, right? So it's the
Yeah,
alternate.
it will be like that, but that is because the function is minus 1 to the I plus j, and since you're increasing this I plus j by 1, you will get alternative plus and minus.
Okay.
Okay, let's do this along the third row. Let's compute the determinant of this example along the third row. What is the third row? This is the third row. And so determinant of this matrix, which I just call A, is minus 1 times determinant of 2, 3, 5, 6. I'll not put any sign over here for now. I'll just write these things. 0 times determinant of 1, 3, 4, 6, and minus 1 times the determinant of 1, 2, 4, 5. Right? Now, these are the terms that are involved, but what are the signs that come along with these terms? So to deduce that, you'll have to look at this entry, minus 1. This minus 1 is actually this minus 1, right? And this is actually A31. Is that
Correct,
fine?
correct, correct.
Yes, sir.
So here I have to put a -1 to the power 3 plus 1.
Sir,
I have
minus
to,
1. Why minus 1? Why not plus?
Because it is the
you,
formula.
so the formula says -1 to the I plus j.
Okay. Okay.
Okay. So in this case, I and j are 3 and 1. So -1 to the I plus j is just -1 to the 3 plus 1.
Sorry to
And
interrupt,
then,
sir. If you show the entire formula once, it is clear for me.
so you want me to show this formula?
Yes, sir.
Okay. So this is the one for just the first row.
छठ खाने के बाद ये भी खा लीजिएगा
Sir,
छठ खाने के बाद खीर खा लीजिएगा
can you please announce that people go on mute, sir? There are a lot of disturbance.
खीर है खीर
Yeah, if you are not asking a doubt currently, please mute your. Only if you have to speak, unmute yourself. Otherwise, please mute yourself. Yeah. So the sign that comes with this is this. So if you simplify this, what you will get is this will come with a plus, this will come with a minus, and this will come with a plus. So similarly, over here, when we are expanding along the second row, this would come with a minus, this would come with a plus, and this would come with a minus. This you can verify. This would be -1 to the 2 plus 1. This would be -1 to the 2 plus 2. And this would be -1 to the 2 plus 3. All right.
Yes, sir.
Okay, so along any row or any column, this can be done. I've done only for 3 rows, but for columns, it is similar. You take the entries, look at the column or the submatrix which is there. When you remove that, the column and row corresponding to that entry, and then do all of the computations.
So,
All right,
sir,
is
So
this
the
clear?
determinant is 6.
yes, whenever we do the computations, always the sign will remain minus as in the formula for any row or any column.
It will be -1 to the I plus j, which accompanies aij. Okay, so this, okay, let me give you the complete formula. So this formula over here was specifically for the expansion along the first row. So if you want determinant along ith row,
Yes, sir.
determinant of A will be summation j going from 1 to n -1 to the I plus j aij m. So what's happening here again? What are these entries aij as I vary j? These are all the entries of the ith row, and they're accompanied with the constant, the scalar multiple, -1 to the I plus j, which will alternate signs as you change I. As you sum over j from 1 to n, this -1 to the I plus j will change signs. And this mij is the determinant of the matrix which is obtained by deleting the ith row and jth column, or the submatrix corresponding to the entry aij. So this is the general formula. Of course, you can find the formula for jth row as well. Sorry, jth column as well. Here I've done ith row, jth column. You can do the same. So this
Yes,
is the
sir.
formula. And once again, even though this is the formula, you don't need to really remember it as this formula is not something that you need to remember. The procedure is that what you have to remember, and then you can just compute it using this principle, right? And
Yes, sir.
yeah, sometimes it is also stated in this way, where you have you don't have this, you just have aij cij. Okay, and cij is just -1 to the power plus j times mij. So this mij is called ijth minor, and cij is called ijth cofactor. So these are all names. Remembering names is not that important, just where it falls into the formula is something that you have to remember. This is determinant along the ith row, or jth column, you can do a similar thing. So before we go into the next thing, I'll just tell you how to do a 4x4 case. Higher dimensional matrices will be very similar in a sense that if you know how to compute the determinant of a 2x2 matrix, you know how to compute the determinant of a 3x3 matrix, right? Because it involves a number times determinant of 2x2. So if you know 2x2, you know 3x3. So similarly, if you know 3x3, you will know 4x4. As a sort of a trivial example, I'll just take this and just do 1010 something. 2, 3, 4, 5, minus 1, minus 2, and 5, 6, 1. Something. Doesn't really matter. I'm not completing the computations. You can do it whenever when you're free. So how will I do this? Once again, using the methodology that we had discussed earlier. Here, it's obviously the first row that is most convenient because it has 2 zeros. So you'll have to actually compute only 2 terms. So for the first row, I'll write it as 1 times, this is the aij, times, strictly speaking, I'll have to do 1 plus 1 because this is the 1/1th entry, times determinant of 3, 4, 5, minus 2, minus 3, 0, 6, 1, minus 1. Then you have a 0 plus 0 times minus 1 to the power 1 plus 2. This will actually contribute a negative sign. But in this case, since we have a 0, it doesn't really matter. So 2, 4, 5, minus 1, minus 3, 0, 5, 1, minus 1. And then I have a 1 times minus 1 to the 1 plus 3 determinant of. At every step, I'm not showing you all of these things, but essentially what you do is just remove the row and column, and whatever you're left with, that is the submatrix that you're working with. So in this case, it will be 2, 3, 5, minus 1, minus 3, 0, 5, 6, minus 1. And the last term being 0 times minus 1 to the 1 plus 4.
Sir, below
Just
3,
one
it's
moment.
not.
Just one moment. I might have made a mistake. Just let me compute. Write this. 5, 6, 1. Have I made a mistake?
Yes, sir. Um,
This
Below
one, is
3,
it?
it's minus 2.
Okay. Okay. So I'm not going to go past this step for computations because this one at this point I think you can do. It is a lot of computations, but it's just routine computations. The person who asked this doubt, is it clear to you how to proceed?
Yes, sir. So just to clarify on the first element alone, where you have
Yeah.
mentioned 1 into minus 1 to the power of 1 plus 1, etc. So when it comes
Yeah.
to determinant of the 3 cross 3, again, we follow the same thing, right? Which is like
Yeah.
3
Yeah.
into
So
minus,
if
yeah.
you just look at this thing, this will again be so. So this is just one. So I'll not write this again.
Yeah.
It's just determinant of this thing. What
Okay.
is the determinant of this? This would be just 3 times
3 times,
determinant
okay.
of
So,
minus 3, 1,
minus
0, minus 1, minus 4 times
should
minus
we
2,
expect
0, 6,
this kind of 4
minus.
cross 4 determinant in the exam?
No,
Okay,
no.
thank you. All right, understood. Thank you.
So one question. Hold on, sir.
Almost
Not
always it
erase.
will not be there. And if you get a 4 cross 4, 5 cross 5, it would mean that you have to do something in a easier fashion. Like there will be theorems which will let you simplify this so that you can do that as well. So
Okay.
not brute force your way through so many computations. This is not what we expect.
Okay.
So
Sir,
one question. So when you do the second iteration of the determinant of the 3 by 3 in this particular case,
Yeah.
should we also do minus 1 to the power of, in this case, it will become what? Second row and second column. Do we need to do the same thing
Yeah.
again?
So this thing, when you're computing the determinant of this matrix, now you should not refer to this as an element of this. Is that is what your doubt is?
Yeah. So no, do we need to calculate the -1 to the power of I
You
plus
need to do
j?
a -1 to the I plus j, but
So
here, for example, it will be -1 to the power 1 plus 1 times 3. Okay, so it's like you're computing the determinant of this.
okay. So you
So
have to
so when you
reset the
say,
values.
yeah. So if someone had asked you just compute the determinant of this, forget about all of these things, just compute the determinant of this, what would you do? You would do 3 times
Right.
-1 to the 1 plus 1, right? So the determinant of this does not have the memory or that it comes from some other bigger
Okay.
determinant.
So 3 will take a reset value ij equal to 1 1 for 3.
Yeah. In this
Okay.
matrix,
Yeah. Yes.
you are computing the determinant of this matrix, and in
Correct.
this matrix, the address of 3 is 1 1.
Sure. Okay. Thank you, sir.
Sir, could you please explain what is minor and cofactor?
Minor is just okay. So this Mij is okay. I'm not writing this. This must have been explained in the last week, but this is the determinant of the submatrix which is obtained after removing the ijth, okay, the row and column corresponding to the ijth entry. I'll just explain it with an example. I'll not write the statement completely. So if I'm looking at that 2 minor of this element, if of this matrix, what is the 2 element over here? It is this 3, right?
Yes, sir.
Now, if I remove the row and column corresponding to that entry, I'm left with the 3 cross 3 matrix.
Yes, sir.
So if I remove one row and one column, of course, I'll be left with another square matrix. I can compute the determinant of that. And the determinant of that is what is called the ijth minor. In this case, the 2 minor.
Yes, sir.
And if you multiply the minor with its sign, what is the sign of the minor? In this case, it is 2 comma 2. So the sign is plus. It is -1 to the 2 plus 2. So it is just the determinant of this matrix is the 2 cofactor as well. But if you now look at this element 4, this element, that is a 2 3th entry. The minor of the 2 3 minor would be the determinant of this, but the 2 3 cofactor would be minus of the determinant of this because it comes with the
So,
sign -1 to the 2 plus 3.
so in minor sign doesn't matter and in cofactor sign matters.
Yes, if you multiply the minor with its corresponding sign, what you get is a cofactor.
Okay,
This
thank
way.
you, sir.
Okay, all right.
Hello,
So
sir.
this
Sir, could
was.
you please pardon that point once again, the minor and the cofactor? Actually, I couldn't understand it completely.
Do you know? Did you understand what the minor is?
No, no, sir.
Okay, so if you are looking at the for example, what is
For example,
m?
sorry to interrupt. For example, my minor of 3 3 3. So we can tell 4, right?
Minor corresponding to coordinates 3 comma 3 is the determinant of. So what is 3 comma 3? The element at 3 comma 3 place is this -3. Is that fine?
Uh, yes. So which means the -3 is
So
the minor of 3 comma 3, right?
no. You have to compute the determinant of this submatrix. You have to look at the 3 3th entry, and then you have to construct the submatrix which is obtained by removing the row and column corresponding to that entry. What you'll be left with is 1 0 0 2 3 5 5 6 minus 1. And how did I get that? I got it this way.
Okay. So it is a determinant value removing the row and column. Okay.
Yes. So that is the minor. Now what is C33? This is -1 to the power 3 plus 3 M33. Okay, this write it as M33. And in this case, it's just M33 because the corresponding coefficient is just +1. For 3 4, for example, it would have become the negative of the 1. Is that fine?
So C will
Got it, sir. Thank you.
tell the sign, give the sign, and M will give the minor.
Yeah, minor multiplied with the corresponding sign is the cofactor.
Okay.
Shall I proceed? Is that fine?
Hello, sir.
Yeah.
Sir, can we also deduce this pattern that we do not have to compute this cofactor always? Like if we are able to the sign pattern, if we see, so the first row of any n cross n matrix will start with plus and then go alternatively minus plus plus minus like this. And from the second row, it will start from minus plus and the same pattern will follow. Can we deduce that?
Just one moment. Minus plus minus plus. Yeah, in this case, that will always happen.
That will always
So
happen because I plus j.
right.
So first row is 1 means it is moving I plus j. So 1 1 moving. So the alternative pattern
Yeah,
will be
here you'll
always.
have this will always be there. So sorry, what am I doing? So you'll have plus minus plus minus. In this
And then minus
case, you'll have a minus plus.
minus.
Yeah, it'll if you can remember it in whichever way you want. If you find that this is easier, this will always be plus because it will be 1 plus 1, and then it will always alternate. This will always be minus because it will be 1 plus 2. This will be 1 plus 3, so this will always be plus. So the first entries will always be like this, and then it will alternate as you move across the row. If this is what helps you remember it, that's fine. But minus 1 to the I plus j is, in my opinion, just as easy.
Okay, sir.
Yeah. Okay, then I'll proceed. We have spent a significant amount of time on this.
Sir,
If there are
please.
more doubts,
Yeah, please.
let's take it up at the end if there are more doubts. All right. So yeah, what is the use of this property is in problems like this one, where there might be specific rows along which your computation, your work will be easy. And then later, when we see reduced forms, you'll see that uh, converting the matrix into a certain form will always help. And that is in some way related to this. Right? That is about the computing of the determinant. And if you want to remember the formula, it is this. Now, the second property.
Sir, kindly pardon that minor and the cofactor part.
Is this part not clear yet?
No, sir.
You want me to repeat this minor and cofactor thing?
Just quickly, yes, sir.
Can we take it up at the end, please?
Sure, sir.
Yeah. Okay. So the second property is that changing, or let's give the more property, product of determinants is the determinant of the product.
You have a nice handwriting, sir. Cursive, you are right.
Thank you.
Yes, I'm also like to say.
Yes, sir. They have great handwriting.
Right. So if I have two m cross n sorry, in this case we're talking about only square matrices. So let's take two n cross n matrices, A and B. So what in for numbers, for real numbers, if x times y is equal to 0, what are the possibilities?
Sir, either x is 0 or
Either
y
X
is 0
or
or
Y is
both are
0.
0.
So okay, now that is for numbers. This we know, everybody knows. Now coming to matrices, if I have AB is equal to 0, does this imply that A is equal to 0 or B is equal to 0?
No, sir, not always because A
No,
and B
sir, not
can be
always.
similar.
Can
If A and B are
Can you give an
similar,
example where AB is 0 but A is both of A and B are not 0?
if A is similar and B is similar, then AB equal to 0.
If you have singular matrices, it's not required that their product is 0. Right?
Sir, for example, in a two cross 2 matrix, 1 0 0 0 and 0 1 0 0.
Okay, let's take up this example.
0 1 0 0.
What is the product of this? First entry is 0, the second entry is 1, 0, 0, right? This is
Sir,
not 0.
if you put it one in the at the end, sir, at the last place.
Yeah, that will work. So this would be 0, 0, 0, 0. Both of these are not 0, but their product is 0. So in general, this is not true, that if the product of two matrices is 0, that one of them has to be 0. That is not true. But what is true is both, at least one of them must have determinant equal to 0. And that is because of the property that determinant of AB is equal to determinant of A times determinant of B. Okay, this is the property. The use of this property will come a bit later. Or, well, just while computing the determinant also, sometimes this is useful, and you can, in problems, if it is specifically designed in such a way that you have to use this property, then you can use this property. But the relevance of this comes much later. Right now, you're just learning how to do things, and where they're applicable will come a bit later. Okay, so the product of the determinant of two matrices, both of them have to be square matrices of the same order. Only then this thing makes sense even, right? If I have A to be n cross n and B to be m cross m, I can't even multiply these things. And if they are m cross n, then this term doesn't make sense. In only
Not a.
Sorry.
Only square matrices have determinants.
Yes, only square matrices have determinants, and in this case, they have to be of the same order as well. You can't have a 2 cross 2 and a 3 cross 3. Then this product AB doesn't make sense. So that's why these are both n cross n matrices in general. And the proof of this will not be given. You can look up a standard text if you want to know the proof of this, but what we are interested in is just the
Sir,
property.
it is already in the week 1 lectures.
It is there, is it? Okay.
Yes, sir.
Probably for 2 cross 2 or 3 cross 3, the proof
Yes,
can be
sir.
given just by brute force, but then for
Yes,
an n cross n, it
Sir,
might not be as easy.
for even for this example also, for A determinant is 0 and for B determinant is 0. So we can
Yes.
say 0 into 0 again 0. We can
You
prove
can
with
say
this.
that. What do you intend to prove with that?
Determinant of A is, if it is A, 1 0 0, 1 0
This
0
is
0,
A, this is B. Yeah.
the determinant of A is 0 and determinant
Yes.
of B is also 0.
Yes.
Right, sir?
You can conclude that determinant of AB is 0, yes, but you cannot conclude that AB itself is 0. You can have matrices, non-zero matrices with 0 determinant.
Okay. Yeah.
Right?
Okay, for determinant B also it is 1, sir. It is 1. 0 into 1, 1, I think.
0 into 1 is 0. So
Yeah, 0, 0, sir. Sorry. 0. Again,
yeah.
we did the same. Okay. Thank you.
Yeah, the property you need to remember is just this. And there are some consequences of this determinant of A to the n being determinant of A to the power n. You're multiplying the matrix n many times, which you can do for a square matrix. The law of orders, all of that is not disturbed. And that is an n-fold product. And the determinant each time splits. Karthik, can you mute yourself? Yeah, thank you. And you'll get n times the product of determinant of A. So you'll get this side. And we will be talking about inverse of a matrix in much more detail a bit later. But inverse of a matrix, suppose I have a matrix A, then it is not always that I have a matrix of the form B such that this happens. This may not be immediately clear to you. Once again, if you go to real numbers, if I give you a real number x, does there always exist something that I can multiply with to get 1?
There is always a 1 by x that exists for that number.
So the candidate would be 1 by x, but if this x was given to be 0, then there is nothing, right?
Yeah.
Yeah.
Then the answer would be indifferent. Yeah.
Yeah, so you cannot find for all values, this is not true, that there exists a number which, when multiplied to the given number, gives you 1. But as long as it is non-zero, such a thing exists. So similarly, in the case of matrices also, you cannot always find a B such that A times B is identity. In the case of matrices, the role of 1 in real numbers is played by the identity matrix. And I hope you know what the identity matrix is. It is just ones along the diagonals and zeros elsewhere for any order, but for 2 or 3, you can just explicitly write it down if you want. And it so happens that, so this guy is called A inverse. If such a thing exists, it is not always guaranteed to exist. But if it exists, it is called A inverse and is denoted like this, A to the power minus 1. Now, what is the determinant of A to the power minus 1? If it exists,
So 1 upon determinant of
1 by
A.
A.
yeah. So to deduce that fact, you see that A times A inverse is identity by definition. By definition, A inverse is the matrix such that when you multiply it with a given matrix, it gives you identity. Now, if I take the determinant on both sides, I'll get determinant A inverse is determinant of I, of whatever order it is. I n cross n identity matrix. Now, what is the determinant of the identity matrix?
So
One.
1.
One sir.
Yeah. So, if you want to quickly see why, if I expand along the first row, it will be 1 times determinant of this n minus 1 identity matrix. Once again, I'll have expanding along the first row, I'll get a smaller identity matrix. It will be 1 times determinant of n minus 1 cross n minus 1, which will be in turn 1 times determinant of n minus 2 order thing, and so on. You'll just get 1 times 1 times 1, which is 1. And that I think you already know this argument, but just if you don't, just follow this. So on this side I have 1, and on this side what do I have? Determinant of A times A inverse is, by the product rule, determinant of A times determinant of A inverse. So the determinant of A inverse is equal to 1 by determinant of A. So for the inverse to exist, there is a condition that the determinant of A should not be equal to 0. So determinant A equal to 0 matrices are called singular matrices.
Why is the name singular, sir, for the matrix which has determinant A is equal to 0?
The nomenclature
Okay,
etymology,
understood.
I'm not sure about.
Okay.
Then A is called singular. Just one moment. Yeah.
So whatever you're telling us now, are these the properties of determinant or like under what
So this is a property of the determinant.
properties of the determinant?
And this is a consequence of what I'm writing below. This is the consequences of that property, some of the consequences.
Could you scroll
So,
up once? Could you scroll up?
further?
Enough, sir. 1 minute. Okay, sir. Yeah.
Well, the better way to write this would be the determinant of the product of matrices is the product of the determinant of the matrices. But you understand what I mean? Yeah. So this singular and non-singular matrices will keep making an appearance. So this is a name that you need to remember.
So
And
will
there are
you
some other
upload this?
properties.
Hello.
Yeah, go ahead.
Sir, will you upload this PDF or not?
Yes, yes. There's a link in the sheet that is shared to you, which directs you to the live session notes folder.
Yes.
It should already contain the week 1 notes, and this will also be there.
Okay.
Yeah. So this is property 2. Then property 3 is that switching a row with another row. So I'll be stating the things as row operations. The same thing will be valid for columns as well. You can just make the corresponding statement for the column, switching a column with another column. Changes.
Won't change determinant.
The sign of the determinant. Right?
Sir, I didn't get that inverse part.
Inverse part, we'll be taking up inverse later when we have to solve a system of equations. I'll make it more clear there.
And sir, what about that determinant of A part and then determinant of A whole raised to power n?
Okay, so if I have a square matrix, I can multiply it with itself any number of times. Is that fine?
Yes, sir.
So if I let's say have A, B, C, D, a 2 cross 2 matrix, I'll just quickly tell you what this means. If I have A, B, C, D times A, B, C, D, if I do this n many times, okay, I multiply it with itself n many times, and then I want to find the determinant of this product. Since the product of the determinant of the product is a product of the determinants, what I'll get is determinant of ABCD times determinant of ABCD, so on. This will also come up n times.
Yes, sir.
Right. So the determinant of the n-fold product, which is over here, is the n-fold product of the determinant. So this is a real number, right? Determinant of A. That is multiplied with itself n many times. That happens to be the determinant of the n-fold product of the matrix itself.
Okay, sir.
So in the exam, if they ask what is the determinant of a matrix of A cube, then what we just need to do is find the determinant of A and then compute the power to the cube. Is it?
Yes.
Okay.
Yes. Yeah. If you have something like, let's say, I'll erase this, but just for something like this or A to the 60, something like that. Okay. Now, if you want to solve this first, that will take Herculean effort. If it's even possible within the time frame of the exam, that is not going to happen. So what you do is write it as determinant of A to the power 3. Well, plus 16 will come. You know why, right? Times determinant of B. So maybe a trick question would be to give a matrix of determinant 0 and then tell you to calculate this. So you don't need to really do all the computations, knowing that there will be a determinant B outside. So this is B transpose. The transpose of the determinant of the transpose is again it's just the determinant. So this part will be 0 and this answer will be 0. This is just a question that I made up on spot, but here you see why the property is important or can be.
Thank you, sir. And you will teach us what is a transpose in the upcoming series.
Was transpose not taught? Should have been taught in week 1, right?
It's taught.
Transpose is nothing but switch, like columns to rows and rows to columns.
Yes, columns to rows and rows to columns.
And a determinant of such a converted transport matrix is 0, is it?
No, determinant of A transpose is equal to determinant of A.
Oh, it is equal to, okay, thank you.
Yeah. I thought even that property is discussed. Is that property not discussed?
It was discussed in previous.
Discussed.
It is discussed, right? Oh.
Sir. Yes.
We saw transpose matrix, but I didn't know that the determinant of the transpose of a matrix is equal to the determinant of the matrix.
Okay, I'll quickly tell you something about that a bit later. Let's finish these properties, please.
Sure, thank you.
So, okay, this is very straightforward. The property sort of self-explanatory. So if I, let's say, just have this.
Sir?
Yes, just one moment. If I have the determinant of this will be negative of determinant of, this is just an example. 0, 1, 0, 1, 0, 1, 2, 3, 4. What did I do? I just switched these two rows. I exchanged row 1 and row 2 and I got this. And how will the determinant change? It will change by a minus sign. Let us just verify this property in this one case. So what is the determinant of this? I'll expand along row 2 because there is only one entry there. And the sign corresponding to the 1 over there is minus 1 to the 2 plus 2 times determinant of 1, 1, 2, 4. I'm doing this over here. And this is nothing but 2. Is that fine? Or is it a little fast?
It's fine.
Sir, please explain once again.
Yeah, I'll come to that. So here, the determinant of this with a negative sign is minus of minus 1 to the power. Now here I'm doing along first row. So that's just 1 plus 2 times 1 times determinant of 1, 1. So there is a minus 1 over here, there's a minus 1 over here. So both of them cancel each other out and this will just be 2. Both of them are equal. This is just a demonstration of that property. So here what I did was I just expanded along, I computed the determinant along this row. The only relevant term will correspond to the term corresponding to this entry, this 2, 2 entry. And for the 2, 2 entry, I'm taking the entry, I'm multiplying it by the corresponding sign and taking the determinant of the submatrix, or I'm computing its minor. So that's how I got 2. On the other hand, I'm computing this side by taking the minus sign which comes over here and then multiplying it by the determinant of this, which I'm computing along the first row, wherein the only relevant term is the 1, 2 term. 1, 2, the term with coordinates 1, 2, which is A12. This is A12. This is the corresponding sign. And the determinant of this is what needs to be computed. And in this case, we can see that RHS and LHS are the same. Is that fine? You don't need to raise your hand and wait for me to ask. Once I'm done doing the calculation, you can just speak up.
So I wanted to ask that just like we made a one switch of the rows. So does this sign depend on the number of switches we made?
Yeah, each switch will correspond to one sign change.
Like we did one switch, row switch, so we get a negative sign or whatever
Yes.
means it is positive, then it will be negative, and negative will be positive. Then if we do another switch, like even if we re-switch the row that we have done before, so it will get the opposite sign. Am I right, sir? Like odd even
Right.
things.
Right. So if you switch once and then switch back, you're actually not doing anything. So the determinant has to stay the same. Or if you think about it as two switches also, you will see that it will become negative of the determinant, which is also the same.
Thank you, sir. Got it.
Is it the same for columns as well?
Yes, that's what I was saying earlier. Here you can replace this with column and column. This once again follows because the determinant of the transpose is the same as the determinant of the matrix. And if I have a transpose and expand along a row, it is the same as expanding along the column of the original matrix. Do you understand that statement?
Yes. So one more thing, can we switch a row to a column and a column to a row?
How would you do that?
Like switching the first row with the okay, but the one will be remaining the same.
Yeah, that you can't do.
Yes.
I mean, logistically also it is not possible, but yeah, to give you a straight answer, no. The row with a row or column with a column.
You have to do that, the matrix has to be transformed, right? You cannot do one single row.
You can do a row with a row or a column with a column. Let's leave it at that. Yeah.
In transpose, we can do the entire matrix. Row with column, column with row, sir.
Well, transpose means it's like taking reflection along the diagonal. You could think of it that way as well. Or you can take the rows become columns and the columns become rows. So it's not that one row is becoming a different column. It's not like that. You're not switching things there. Anyway, that's all about this property. Let's go to property 4. This was property 3, right? Yeah. Property 4. Maybe I'm missing one property. Let me just check. Adding multiples of one row to another. Okay, there is one more property. I'll discuss that. That's property 5. Multiples of one row to another row. Once again, same thing is applicable for columns as well. One row to another row does not change the return.
Sir, we are just revising week 1, or we are.
This is 2. This is 2.
This is in week 1 also.
This is part of week 2 as far as I know.
Okay, sir.
For general n cross n matrices.
Like sir, we have been taught the properties in the week 1 itself, and in week 2 we have been introduced with the Kramer's rule. The starting.
The first section, the determinants part 3 of week 2 concerns these properties that I'm discussing right now.
Okay.
So let me just finish this quickly then. So now what does this mean? If I have a row, let me just take an arbitrary matrix of order 3 cross 3. This has some determinant. It says that this is the same as, this is one instance of that thing, a plus dd, b plus d, c plus f, d, f, ghi. And in examples, I might be giving you 3 cross 3, but all of these rules are applicable for matrices of any order. Now, what have I done over here? In this matrix, what I have taken is, I have taken this row 2, DEF, and multiplied it by a scalar t, and then added it to the corresponding elements in row 1. I take row 1 and add multiple of another row to it. And it so happens that the determinant does not change. Instead of symbols, now let's take up an example. Let's take 2, 1, 1, 1, 1, and 0, 5, 6, something like that. Just to demonstrate in what cases this would be useful or applicable. In order to compute the determinant, you could go the straightforward way by doing 2 times the determinant minus 1 times the determinant plus 1 times the determinant. Or you could use this property and you say this using row 1 minus row 2. So adding multiples means the multiple could be negative also. So you could subtract multiples as well. So what do? I subtract row 2 from row 1. I get a 2 minus 1, 1 minus 1, 1 minus 1. And the others remain unchanged.
Sir, is this t a scalar?
T is a scalar. T is a scalar meaning a real number. Any multiple, you can multiply any row by that number and add it to another row. So this t could be any real number.
In this case, t is equal to 1, right?
In this case, t is equal to minus
1. Minus 1.
Yeah, I'm taking this row, multiplying it by minus 1. What do I get? I get minus 1, minus 1, minus 1. I add it to row 1. So what is, okay, this is determinant is equal. The matrices are, of course, not equal. But by doing this, what I have is a much simpler matrix. Immediately, I can see that the determinant is 1.
With one calculation, you can do the determinant.
So by doing some operation on the rows, I have significantly reduced the amount of calculations that I have to do. And that is thanks to this property. If I take a given matrix and I can smartly find multiples of another row, which when added to some other row, gives me a simpler form for which computing the determinant is easier, then I'm in good shape. And that is why this property is powerful. Is that clear? Is this example clear?
Sir,
Yes, sir.
can you do this in 2 by 2 matrix?
It's pretty much the same, right? If I have, let's say, 3, 2, give me minus 2, the determinant of this, you can compute it directly. That is minus 6 plus 4. So in the case of 2 cross 2, the simplification is not that significant. But anyway, let's do. We'll add the second row to the first row to get 3 minus 2, 2 minus 2, minus 2, minus 2, and then determinant of 1, 0, minus 2. Here, of course, this is just minus 2. And these two things match. Here also you can check that this also has determinant 1 if you want. You can do that at your leisure.
Sir, in this matrix, you took that scalar as 1, is it?
Yes, yes.
And
I took row 2, multiplied it by the scalar 1, which is unchanged, and then added it to row 1.
Okay.
And
Row 1 becomes row 1 plus row 2.
in matrices, when we are doing the row operations, if we are first operation is along the rows we are supposed to all the operations through rows only. We can't do like one by row and one column like that, right?
As long as you're keeping track, it's fine. You cannot do it simultaneously, as in you once you do a row swap, you
Yes.
can after that with the new matrix you can do a column swap. And as long as you're keeping track, okay, here you are adding multiples. So once you do addition of multiple of one row to another, then you have to use that matrix, and there you can do column additions as well. What I mean to say is, so if you have A, B, C, D, you can convert this to A plus T1C, B plus T1D, CD. And then in the second step, you can make it something like A plus T1C. I'll keep the first column as the same, but I can add some other multiple, B plus T1D plus T2 times A plus T1C, because this is the new column, D plus T2C. Do you see what I've done over here? In the first step, I've added T1 times second row to the first row. And for the matrix that is obtained, I have added T2 times the column 1 to column 2. And the column 1 now in the new matrix is A plus T1C. So I have to do T2 times A plus T1C.
Okay, in that case, when we are swapping the rows, in the determinant will be minus, as you said. So in the new matrix, if I am swapping the columns, again the determinant will be changed the same way by rows we are doing, or it will be different.
Row or column swap, both of them will change the sign by -1. So this is what you're worried about, the switching of rows and columns, is it?
Yes, yes. First row, if was
Okay, let's take an example. 2, 3, 4, 5 is this. This has determinant -2, right? Now, if I do 4, 5, 2, 3, this has determinant +2. It has changed the sign. Now, again, if I do a column switch, which is 5, 3, 4, 2, what is the determinant?
It
It has
will be
become
two.
minus. It has become -2 again. So here this was 2, this became -2, or wait. Minus 2
-3.
plus 2 minus 2.
Sorry, 2.
And
Yes.
is this clear?
Yeah, clear. Thank you.
I'll erase this, alright? This is what out of place.
So is it necessary to take a scalar as -1 or 1 only?
Not necessary, not necessary. Yeah, here, okay. Let me just do.
I guess if we take like scalar 2 or more than 2, then I guess the matrix get doubled.
Let me just do this. Just to that's actually yeah, I've just used +1 and -1 in the examples that may be confusing. So let's do this. -10 plus 8. So this thing is -10 plus 8, which is again -2. But then I'm adding 2 times the second row to the first row, and yeah, the rest of the stuff is the same. But here I've added 2 times. You can add fractional times also. It doesn't really matter.
Sorry, sir. What's that? 2 times what?
R2. This is 2 times R2. I've added to this. I've added -4 to both entries, right? Which is 2 times the second row that I've added to the first row.
Okay.
That is another property. And the last property is, what is it now? 5 or 6? 5. If a row, once again, slash column, is multiplied by a real number t, determinant gets multiplied out by the same number. In this case, we are not multiplying the entire matrix by some real number, but if you just multiply a single row by some real number, that matrix will have the determinant t times the original matrix. So if, once again, example, if I take a matrix 2, 1, -1, 3, and then if I take 4, 2, -1, 3, I'm just taking simple examples. The determinant of this will be double the determinant of this, because what is the difference between this matrix and this matrix? Row 1 is multiplied by the number 2. So your determinant also gets multiplied by the same number. So here the determinant is equal to 6 plus 1, which is 7. Here the determinant is 12 plus 2, which is 14, as expected. So the determinant is double of this. Why? Because here R2, I'll call this guy R1. R1 tilde, which is the row of this. This is R1, R2. Is 2 times R1. And R2 tilde is the same. So every time a row is multiplied by a factor, the determinant gets multiplied by a factor. This is somewhat easy to see if you interpret it geometrically, but we are not going to do that right now. Maybe in the next session, if I have time, I'll discuss that. As a consequence, though, what is the determinant of negative of the identity of a matrix?
-1.
Does everyone agree?
No, sir. It depends on the number of row and column.
That depends on the number of the order of the matrix, the I.
Yeah.
That
What about this one?
One, sir.
This is one.
One.
So it's saying that it is -1 always is not correct. But how can we interpret the negative identity of a matrix? It can be obtained by multiplying each row by -1. Is that fine?
Yes, sir.
So if I take just the identity matrix, whatever its order may be, and then I convert it by multiplying each row with a -1. I'll get -1, 0, 0, 0 over here. The second row is also -0, -1, 0, 0, and so on. I'll get this. So I want the determinant of this. So how many -1s have I multiplied two rows? I have done it n many times. Correct?
And yes, sir.
So determinant of -i of order n. This -in just means minus the negative of the identity matrix of order n. This is -1 to the power n times determinant of identity. And what was determinant of identity?
1.
That was just 1. So this is -1 to the n. So this is a common pitfall that people think the determinant of minus identity is -1 because it's negative of the identity, but that's not the case. And it actually depends on n. And that is a consequence of, this can be seen as a consequence of this property.
So, in this specific property that you explained, what if one of the row in a matrix is multiplied with a one scalar and another row is multiplied with a different scale, a different real number? For example, row 1 is multiplied by 2 and row 2 is multiplied by 3.
Okay, let's do that. It has to, the determinant has to get multiplied by 2 times 3, right? You can do it stepwise.
Okay.
So if I take a matrix, let's say 1, 0, 3, 4, well, bad matrix, but okay, let's just take. And you say you multiply it by 2, 0, and 9, 12. Is this something that you, right?
Correct.
So this is 4, this is 24. So this becomes times 6, and that should not be surprising because if I take 1, 0, 3, 4, and then I just do one step of the property, I just do this. This would have determinant 2 times because it is multiplying one of the rows by. So let me call this A1, A2, and A3 is I take this matrix and I multiply the second row by 3. So I get A3. So what is determinant of A3 is what we want. But forgetting about this factor, if I just look at this second step to third step, what I get is this is 3 times determinant of A2.
Okay.
Now, if I don't see this part, I just see how I got A2 from A1. The determinant of A2 is 2 times the determinant of A1.
Understood.
So this has to be 6 times, as expected.
Thank you, sir.
All right, so that's all about properties of determinants.
Sir, this row can also be changed to columns, right? This multiplication, scalar multiplication.
Yeah, you can multiply columns if that is what you're asking.
Yeah.
Yeah, so that's where.
What if we interchange 2 rows or 2 columns? What will happen to the determinant?
The sign changes. That is what we discussed over here. So switching a row with another row will change the sign of the determinant.
Oh, yeah. Thank you.
Okay, that's properties of determinants. Now we have seen what determinants are, how to compute them, and what are their properties. Now we'll see one of the applications of the determinant. Now we'll come back to sort of the goal that we started out with, solving system of equations. I'll just write it as Ax is equal to B. A is a n cross n matrix, X is an n vector, and B is a m vector. Now the simpler case, the first case that we will deal with is the simpler case where a coefficient matrix is a square matrix. So for this, you have 2 methods. The first one is this is a simpler case that we deal with when A is a square matrix. What does it mean to say A is a square matrix in terms of number of equations and number of coefficients? Can someone tell me what A is a square matrix represents?
The number of coefficients equal to the number of variables unknown.
Yeah, the number of equations and the number of uh,
Number of
variables are the same.
equations too.
So if I have a coefficient matrix A of size m cross n, what is m and what is n in terms of the system of equations, like in terms of the terms involving the system of linear equations?
Rows and column.
Rows and column.
No, m is the number of equations and n is the number of variables.
Correct. So m is the number of equations and n is the number of variables. So often for unique solutions and all that, you this is not necessary, but when you have number of equations equal to number of unknowns, that is the interesting case. So that is what we'll first deal with. Then we'll see the general case as well. But first, for the rest of the session, I think we'll only have time for that much. For Kramer's rule and another application of the inverse, we'll have this A to be a square matrix. Right? So using Kramer's rule to find the solution to a system of equations. I'll just explain the method and I'll give you an example. So when can Kramer's rule be applied? First, we have to state that. When to apply, when can be applied is, of course, I'm repeating this. A is a square matrix and determinant of A is non-zero. Only when determinant of A is non-zero can you use this method. And if you remember, this is called non-singular. And how to apply? Obtain matrices AXI by replacing column I by B. Is there a problem with the mic? Is it
No,
not
sir.
clear what I'm saying?
No,
No,
it's
no.
clear, sir.
Yes, sir.
Okay, okay. Obtain matrices AXI by replacing column I by B and then use XI is equal to determinant of AXI divided by determinant of A. Of course, we have made sure that the denominator over here is not 0. So this actually makes sense and all that. As it is, this might not be making sense to you right now. Let's take up an example. Let's take a 2 cross 2 example and 3 cross 3 and everything follows in a similar way. I don't even know if this would be a nice solution, but at least we'll get some fractional solution. 2x plus 3y is equal to 6. Let's do 5. X minus 2y is 3. Let's see. This is the system of equations. The number of equations is equal to the number of variables. So you are in a square matrix setup. In fact, what is the coefficient matrix over here?
2, 3, 1 minus
2,
minus
3, 1 minus 2.
And what is the constant vector?
XY.
XY.
That's the coefficient. That's the variable.
Constants.
This
Okay,
is
5 and 3.
Oh, 5 and 3, sir.
5 and 3.
Yeah. So what I'm going to do, if I want to use Kramer's rule, I have to make sure that my coefficient matrix is a square matrix. That is done. And then look at what is the determinant of that. What is that? Anyone?
-7.
-7, sir.
Yeah. That's both of the conditions that need to be satisfied for the use of the Kramer's rule are there. So let's do it. So what does this say? Obtain matrices AXI by replacing column I by B. In this case, I'm going to call it AX and AY. AX is the matrix which is obtained by replacing the first column with B. So what is the first column in the coefficient matrix? It is 2, 1.
2 and 1.
2, 1.
2, 1. So instead of 2, 1, I write B, which is
5 and
5.
3.
5, 3, 3 minus 2. And what is determinant of AX?
Minus 19.
Similarly, I'll do AY. For AY, what do I do? I keep the first column as it is. I
We
replace the
will change
second
the
column
second
by
column.
I replace the second column by B, and then what is determinant of AY?
1.
1.
1. So Kramer's rule says that X is equal to determinant of AX by determinant of A, which is just 19 by 7, and Y is determinant of AY by determinant of A, which is 1 by 7. 38 minus 3, 35 by 7 is 5. 19 plus 2, 21 by 7 is 3. Yeah, this is the solution. You could have done it using the usual method as well, but this is another method.
Sir, in the AX, you took 5, 3, 3 minus 2. So
Yeah.
3 minus 2 is the Y form, right?
So, okay, if this is confusing, let's just call this x1, x2, x1, x2, and let me keep consistent with the steps that I've described earlier. X1, x1, x2. This is x2. All right. So here, if you want to do ax1, all you need to do is replace the first column. For the first variable, you replace the first column by b and keep this as it is. For the second variable, what you do is you take a, keep the first column as it is, replace the second column. For the ith variable, in general, for an n cross n setup, what you do is you construct I many matrices wherein column I is replaced with the constant vector. Everything else is the same.
So where is the minus 7 coming? Determinant of A minus 7 first step.
Determinant of A is minus 7, right? It's just minus 4, minus 3.
Sir,
Is that all right?
yeah, where do we use Kramer's rule, sir? When we subtract them, it's very easily we can find x1 and x2 values. Then what's the need of doing all of this? And where do you use specifically this rule, sir?
The practical applicability of Kramer's rule is something that I don't know about. And for 2 cross 2, as you say, it might be easier to just solve it by hand. But for higher dimensional things, this will be, for a human also, this will be easier. And if you want to encode it into a computer, let's say, I think this procedure is more algorithmic. You'll see that Gaussian elimination is still better later on. But this is one of the ways.
Okay, sir.
You can code this into a computer, right? You can just say that these are the entries. Then you compute these. Computing determinant is something which you can do the formula for. Replacing certain entries of a matrix is something that you can easily do, and then you can actually write at least the pseudocode for this.
So if the 3 unknowns and 3 equations, then it's easy. Anything beyond that, if you have 4 unknowns and 4 equations, it becomes difficult to calculate. So this is the only way to get them. those four solutions.
This is not the only way, but yeah, this is one of the ways.
Yeah, this is one of the way to anything more
Yeah.
than beyond 3 dimensions is difficult to calculate manually.
Yeah, by hand, well, computing determinants of 4 cross 4 matrices also would not be easy. And it could be argued whether this is easier or that is easier. But this is just one of the ways. And yeah, that's all I leave it at, because I don't know
Better
the
than solving equations.
computing complexity of different methods. I am not very well versed with how to quantify it and all that. You can look up books on that. You can look up on the internet which is the most efficient method and all that. All right, so this I'll just stop with this example for Kramer's rule. You just need to know when you can apply it and how to apply it. I have done it for a simple 2 cross 2 thing. For the 3 cross 3 thing, it will be similar. You will just have three matrices AX1, AX2, AX3, where you will replace columns 1, 2, and 3 respectively by the constant vector, and then compute those three determinants and then divide by the determinant of the original coefficient matrix. So another way to compute the solution, to obtain the solution of AX equal to B when A is a square matrix, is using the inverse. Once again, when can you use this is identical. A is a square matrix. And determinant of A is not equal to 0. These are the two conditions once again that you have to use. But now we'll get into the inverse of a matrix. Inverse of a matrix I briefly mentioned earlier. I said that in real numbers, if I'm given an arbitrary x, can I always find a number which I can multiply x with so that I can get 1? The answer is yes, as long as x is not equal to 0. So the same question for matrices is that given A, let me call this n cross n matrix A. A subscript n cross n just means that it's an n cross n matrix. Alright, it's nothing more than that. Given A n cross n, a matrix B such that AB is equal to BA is equal to identity of order n exists if and only if determinant of A is not equal to 0. So determinant seems to be the quantity which determines whether a matrix has an inverse or not. So if I have a real number x, what is the number that I would multiply over here? It is 1 by x. Now that is the inverse of x, or x to the power minus 1, right? So this is in the same spirit we call this matrix B as the inverse. Inverse does not always exist, and whether the inverse exists or not is determined by the determinant. If the determinant is non-zero, then the inverse exists. Is this part clear?
Yes,
I've
sir.
not given a proof
Yes,
of
sir.
this statement, but I'm just telling you to take it as a fact. The proof of that, I think the professor has given in the lecture videos. You can go and take a look at it whenever you want. We are not going to look at the proof of that, but we'll just work with this much. If the determinant is non-zero, there is a matrix satisfying this property that AB is equal to BA is equal to identity. And conversely, if there is a matrix such that this equation holds, then determinant of A is not equal to 0. That part is relatively easier to see just by the product properties. Once again, I'm not going into the proof, but you can just take the determinant of this equal to determinant of this, and you can deduce that if AB is equal to identity, then determinant of A should necessarily be non-zero. But the other way is also true. But now we are in a setup where A is a square matrix and determinant of A is not equal to 0. So the inverse of A exists, correct? I am given the system of equations Ax equal to B. And since this is there exists an inverse. So the inverse of a matrix, inverse of A is denoted A. Okay, so we don't use this B just to so that it how it is related to A. We use the symbol A inverse, A to the power minus 1. Right? Now back to system of equations. If I'm given a system of equations Ax is equal to B, such that the determinant of A is non-zero, A is a square matrix and determinant of A is non-zero, I multiply both sides of this equation by the matrix A inverse. Someone's mic is on. Can you please mute yourself? Yeah, thanks. A inverse times B. But what is A inverse times AX? Matrix multiplication is associated. Right? So this will be A inverse A times X.
X
And this
only,
side you
sir.
have. So A inverse A is just identity, and identity times X is just X. So X is equal to A inverse B. At least symbolically, this is fine, right?
We can even
Is
say
there,
X is equal to 1 by A B, sir. A inverse is
what is 1
1
by
by,
A?
sir?
So if I have a matrix A is equal to, let's say, 2, 3, 4, 5, hopefully, yeah, this is non-zero determinant. What is 1 by this?
Sir,
What is 1 by A?
yeah, determinant. In the time, we can say 1 by determinant A, right?
1 by determinant A will not be equal to B, no? Because let's say this is an n cross 1 matrix. A inverse will also be a n cross n matrix. Okay, the dimensions match because this is a square matrix. But yeah, it is not just the number.
Okay,
1
sir.
by, so A inverse is a matrix which when multiplied to A gives you identity. I have not told you how to calculate the inverse, but assuming that you know how to calculate the inverse, you have the solution. Is that fine with you?
Yes, sir.
Okay, sir.
If a matrix such that A inverse is equal to identity exists, then the solution to the system Ax equal to B is X is equal to A inverse B. This is the first statement that I'm making. Is this fine with everyone?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Now, so the point is, how do I compute A inverse? How do I compute the matrix which happens to be the inverse of this? I can't, for example, if I just look at this guy, I can't just say 1 by this. This doesn't make sense, right? This is not a matrix, and you don't know what this. A number by a matrix is absurd. So we need a matrix which satisfies this property. So the procedure to compute the inverse is as follows. I'll not write down step by step in language. I'll just take an example and then later on, if required, I'll write it down. Right? Let's take this example itself. 2, 3, 4, 5. So here your cofactors and all that come into picture. So this is my matrix A. What I need to do is look at every element and compute its cofactor. So what is the cofactor of 2?
So 5.
5.
So let me call this C11. What is C11?
5.
It is minus 1 to the power 1 plus 1 m1. And what is m11? That is 5, and this is 1, so this is h5. What is c12?
Minus 4.
-4.
This is minus 1 to the power 1 plus 2 m 2, which is
Minus 4.
what is c21?
Minus 3.
-3.
And c22 finally
2.
is just 2. Now this matrix I'll call the cofactor matrix. How do I compute the cofactor matrix? By just writing the cofactors of the corresponding elements. And then take the transpose of the cofactor matrix. What is the transpose of this matrix?
So 5 minus 3 minus
5
4 and 2.
minus 3 minus 4, 2.
This is called adjugate matrix of A. This is just the transpose of cofactor. Now there's one final step, is that we'll have to divide, or we'll have to multiply 1 by the determinant of the original matrix to all entries. That is, you have to multiply this matrix by 1 by determinant of the original matrix. What is the determinant of this matrix?
Minus 2.
Minus 2. So what I have to do is, A inverse is 1 by minus 2 of 5 minus 3 minus 4. Let's just verify that this is correct first, then I'll recap the steps. So what was A? A was 2, 3, 4, 5. 2, 3, 4, 5 times 5 minus 3 minus 4, 2. And there is a constant of minus half outside. Let's leave it there. What does this give me? 10 minus 12. 6 minus 6. 20 minus 20.
Minus 2.
Minus 2. Now I bring the constant inside with the negative sign. What I will get is 100.
Identity matrix.
That's what we wanted, right? This was A. This along with this was A inverse. And A times A inverse is equal to identity is what we got. So to recap, how did I get the determinant? First, I wrote the cofactor matrix, which is literally just the cofactors of the elements. You take each element, you just compute its cofactor. Don't multiply it by the element and all that, just as you do with the determinant. You just do cofactor. So ij entry is just Cij. Okay, so you just take the submatrix which you obtain by deleting the row and column that the entry belongs to, and then multiplied by the corresponding symbol, sign, -1 to the I plus j. And that is how you get the cofactor matrix. You transpose the matrix, what you get is the adjugate matrix, and then divide by the determinant. And what you get is the inverse of the matrix. So A inverse is equal to 1 by determinant of A of adjugate of A, or you could also write it as 1 by determinant of A. I'll just write it as C of A. I don't know if the prof uses a different notation. If he does, you follow that.
So
So
give us
this
a
is
minute. We'll make a note of this particular.
all right. So how to compute the inverse? Once again, compute the cofactors, put it in a matrix, take its transpose, that is the adjugate, divide by the determinant. And all of this works because we have assumed at the outset that determinant is, we will work only when determinant is not equal to 0. The inverse exists if and only if determinant is not equal to 0. So this makes sense, right? Dividing by the determinant otherwise would not make sense. If I have a determinant 0 matrix, then I cannot compute its inverse. But to actually say that its inverse does not exist, you'll have to give an alternative argument, but at least this formula would not make sense for a determinant 0 matrix. But that is not an issue in our case because we have assumed that determinant is not equal to 0. So is this clear, at least the procedure? You will have to do more examples to get used to it, but at least the method is clear, right?
Yes.
Yes.
Okay.
Yes, sir.
So let's try to do whatever this Kramer's rule 2, 3, 1, minus 2, 5, 3. 2, 3, 1, minus 2, 5, 3. So 2, 3, 1, minus 2, x, y is equal to 5, 3. Using Kramer's rule, we did it. Now let's do it using the inverse. What is the inverse of, this is A, this is x tilde, this is B. Let me call this x1, x2 itself to avoid confusion. What is cofactor of A?
Then minus 2.
Minus 2, 1.
Minus 2,
The minus 1. The minus 1.
minus 1,
3.
minus 3,
Minus 3. And 2.
2.
What is determinant of A?
It's a minus 7.
Minus
That was
7,
minus 7. That we knew from before. Now, what is adjugate?
Then minus 2,
adjugate
minus
is
3.
minus
Minus 1
2,
and 3.
minus 3, 1, minus 1, 2.
2. And then, so what is A inverse?
So 1 upon minus 7 and
1 upon
adjugate of
minus
A.
7 by minus 2, minus
Shall we
3.
do this?
Yes, sir.
I just took the minus 1 inside. Now, what does the determinant method say? X is equal to, or x1, x2 in this case, is equal to A inverse B. So, A inverse is this. What am I doing over here is this. So we saw that if the inverse exists, then the solution is given by A inverse equal to A inverse times B. X is equal to A inverse times B. So that's what I'm doing as the final step to solve the system of equations. The B was 5, 3. And that is 1 by 7 times, what is the answer? This is 19, and 5 minus 6 is minus 1. Does that agree with the earlier solution? 19 by 7 and minus 1 by 7? It does. It has to. Are all the steps over here clear, or do you want me to go over it once again?
So it's clear, sir.
Yes.
Please, can you go through it once again?
This particular example I'll take up and I'll tell you what we did.
Okay.
So the coefficient matrix in this case was 2, 3, 1, minus 2. Then we calculated the cofactor matrix. How did I calculate the cofactor matrix? For the first entry, for example, you look at this and there's only minus 2 and it comes with the sign plus 1. So it is as it is. For the second entry, we look at this, which is 1, but it comes with the sign minus 1 because of minus 1 to the 1 plus 2. Similarly, for the third entry, we look at 3 with a minus sign. And for the fourth entry, we look at this with a plus sign. Same thing, similar things we have done for the determinant, but these are the cofactors. So we put them all together to get the cofactor matrix. And then we transpose that to get the adjugate matrix. And that is this, where So this column has now become this row, and this column has become this row. That is how you get the transpose. You make the rows into the columns. So then I divide by the determinant, or I do 1 by determinant of A. In this case, the determinant was known to be -7. So here, strictly speaking, I could have done one more step where I did just 1 by -7 times the adjugate matrix, but I just put the minus inside and I gave this guy a negative sign. So that is the computation of the inverse. And once I compute the inverse, then the system can be solved by just multiplying the inverse of the matrix to B. And one warning is that you should not do BA inverse. In general, matrix multiplication is not commutative in the sense that AB is not equal to BA. As you can verify with many examples that you can just look up some random numbers and most of the time they will not commute with each other. Commuting means the order of operation does not matter. In this case, it does. For real numbers, of course, it does not matter. XY is the same as YX. I'm good. But in matrices, the order of operation does matter. So it's actually A inverse B and not B A inverse. You have to multiply the matrix A on the right with B. And this is A inverse, this is B. And what we get is 1 by 7 times 19, 1. Therefore, x1 is equal to 19 by 7 and x2 is equal to -1 by 7. Is that fine?
Is it simple multiplication we have done there?
Where, in which step?
Hello.
Hello, sir. I
Hello,
have
yeah.
a small doubt.
To get 19 minus 1, we have done the multiplication there from A inverse B.
So A inverse is a matrix, B is a matrix. We have done matrix multiplication. So 2 times 5 plus 3 times 3.
Got it. Thank you.
Yeah, this is a matrix multiplication. This is just a scalar multiplication. You just multiply a real number to a vector. You just multiply to each of the components. So this is just multiplying this into this. And yeah, that's it.
So we see here two methods. Which method is most recommended for easy solving?
I think the inverse method is easier.
Okay,
it's up to you actually. The theoretical part, it just gives you an exposure to different methods. You can use whichever you want in the exam, even if questions of the sort of compute the solution to this comes up. We don't really specify using this method only or that method only. I feel this, on an average, this would be an easier method. There might be cases where Kramer's rule is easier. But then for here, you have to see that we have dealt with a very special case where your coefficient matrix is a non-singular square matrix. So what about the other cases? Then, so for that you have this Gaussian elimination method, which we'll discuss in the second session. And in that case, it doesn't matter whether you have a square matrix or not, and if the square matrix is singular or not. It is something that works for everything. And it is also quite simple once you get a hang of it. And we'll see that in the next session.
Sir, I
So
have
when we
noted
get the next
this. I have
section,
posted in chat box.
One at a time, please. I didn't get either of you.
Sir, I
when
have
we
a question. I have posted the question in chat box. Can you please answer this?
What's a null matrix? You mean singular matrix?
No, sir. Null means zero matrix.
Okay, if
Zero
AB is
matrix.
equal to 0, A is null and B is null, that's fine. A is null and B is not null, that is also fine. A is singular and B is singular.
Can be similar, sir. A can be singular and B can be singular.
You mean A is singular or B is singular?
A singular and B singular, but it can be possible that singular into singular matrix can be a zero matrix?
Yes. So singular, you mean not null. Like the other example that we were discussing earlier, this, it is a product of two non-zero
Singular,
singular matrices whose product is zero.
but both are singular, no sir.
Ah, okay, both are
A
singular. You
and B are
want
both
one
singular.
singular and one non-singular.
यस सर, क्या ऐसा हो सकता है कि एक नॉन सिंगुलर हो और एक सिंगुलर हो, उसका प्रोडक्ट एक नल मैट्रिक्स हो, जीरो मैट्रिक्स हो?
Yes, it is possible for sure. Uh, to give you an example off the top of my head, you want AB is equal to 0, A is singular, B is non-singular,
B is non singular. Yes sir.
and A is not 0. Like 0, the null matrix is also singular, you see. So I can give you a trivial example. You can just have 0, 0, 0, 0 times some, you can have 0, 0, 0, 0 identity is equal to 0, 0. So here you want some non-zero matrix, is it?
समझ गया सर.
So this is
And
possible, but if you want a non-zero matrix over here, that is also possible, but yeah, I'm not.
नॉन जीरो होना चाहिए सर, एक नॉन जीरो होना चाहिए और दूसरा नॉन सिंगुलर होना चाहिए. एक सिंगुलर दूसरा नॉन सिंगुलर, बट नोट बी जीरो.
Yeah, just give me one moment. 0, 0, 0, 1.
क्या ऐसा पॉसिबल है भी, पॉसिबल नहीं है?
Yes, 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 it's possible. It should be. It is very much possible. Yeah, I'll give it to you in the next session.
Okay, sir. Thank you.
Yeah,
Sir, when is the next session?
Thursday. It's always Sundays and Thursdays, unless there is some public holiday or some
Okay, thank you, sir. Very
unusual.
helpful. Thank you
scenario.
very much.
Sir, will it by you?
Next Thursday is mine. Yes.
Sir, I have a small doubt in property 4 that we discuss. If we multiply each element of a matrix, for example, with 2, so will matrix will be double?
Just one moment. What do you mean by matrix will be double? Property 4 is where?
Sorry, determinant will be double?
No.
If we multiply each element with 2?
Okay, that is a good question. I'll give that specific. By the way, it's not property 4, no, it's property 5 probably.
Yes, sir, sorry, sir.
So yeah, property 5 says if a row is multiplied by a real number t, then the determinant gets multiplied by the same number. But what you're asking for is if the whole matrix is multiplied by
yes,
a real number t, right?
Each and every element.
So multiplying a matrix, all the entries of a matrix by a real number t, isn't it the same as multiplying each row by the real number?
Maybe.
So if I take a matrix from A, B, C, D, and I do TA, TB, right? And all those people who are saying that my handwriting is good, you will notice that towards the end of the session, it deteriorates. This can be obtained in 2 steps by multiplying 2 rows, right?
Okay, so it will be 4 times.
It will be 4 times. In general, if I have an n cross n matrix and I multiply all the entries by t, what will be the factor by which the determinant gets multiplied?
T to the power of n.
Yeah, in general, it is t to the power n because there are n rows. So you're doing this multiplying each a row by the factor t n many times.
Normally we say m into m, right? M rows and n columns. So in this case, it's t to the power of m. If you consider it, right?
This is an n cross n matrix, and you're multiplying every element by the scalar t, which is the same as saying you're multiplying each row by t. And how many rows are there? There are n rows. So it is t to the power n.
Okay, sir, got it. Thank you so much.
That is so. Let me write it over here. In general, determinant of t a n cross n is equal to t to the power n determinant of a. Why did I say in general? Because this is a special case of that. Determinant of minus in is what? Multiplying minus 1 to every element of identity, which gives you a factor of minus 1 to the n. You can get TA from A in n steps by multiplying t to each row, one by one. And each of that gives you a t factor, and there are n many rows, so you'll get a factor of t to the n. Yeah. Okay, let's wrap up. In the next session, I'll do the rest of the topics, which is echelon form and the Gaussian elimination method.
Thank you, sir.
And unless there are doubts, I'll stop. We can stop. If there are doubts, please go ahead.
Thank you, sir.
Thank you, sir. Very helpful.
Bye, sir.